what we did on Friday. Yes.
I understood the lecture, but when you like related the rate of change to that little graph, and then like you did the Q on the both sides and you kept on repeating, oh, it's the same thing. I didn't really understand.
Because remember, we're taking limits, right? Definition is a limit. So the limit is a two-sided limit. For example, let's go here. We're trying to define the slope of a tangent line, right? And then what's the idea? The idea was, let's look at the circle. The circle is easier to look at. It's a nicer picture. So we want to make sense of the slope of this green line. So the idea was, okay, by the way, for the circle itself, we do have a nice definition of the tangent line, but this is only special for the circle. The fact that there is only one line perpendicular to the radius of the point, and that's what we call the tangent line. But for any other function, this is not the case. So what was the idea? Okay, take another point away from P. Okay, look at the line that connects P and Q. Let's call this other point Q. And then we know how to find the slope of this line because we have 2 points. We know how to find the slope. So the idea is let's get this point Q closer and closer to P. In this case, I'm doing it from the right, if you wish, or from below, because we're looking at a circle. And then just keep on looking at all the lines that are formed, joining P and the new point Q. And the closer this point gets to P, hopefully you see that the lines, the secant lines, are getting closer and closer to the green line. Do you see that? Yeah. But I could have done that from this side as well. Right? And that's basically what I was saying here. You know, I first started taking my Q here, and then we're going towards P this way, exactly doing the same idea. But you could have started with Q up here, and then go towards P this way. And look at all the secant lines, they will all go to the blue line, regardless. So on the x-axis, then, you know, if Q is on this side, then that means this H here, you know, I mean, distance is always positive. H here really represents the distance, but when you take the limit as H approaches 0, because you want to get close to A, that means we want to make this distance as small as possible. When this distance goes to 0, then your point is close to A. You understand that? But when H goes to 0 in the limit, it could do it from the right or from the left, so with positive or negative values. Okay? The green picture represents when you're doing it from the right. And the black picture represents when you're doing it from the left. The reason why I wanted to do that is because, you know, in the formula we have the plus.
Yeah.
And if I stick doing it from here, then you will say, well, why do you have plus and not a minus?
That's nice.
Well, because you can think of this H as being a variable, and then if you go from the left, it's now negative, and therefore you really have something like this. And if you do it from the right, it's positive, and then you will have the plus. So that's what. Just that I was talking about it, I realized, okay, this is going to be a problem.
I rewatched that part like 4 times, and I was like, uh-oh.
But you see, we're taking a limit, so it doesn't matter,
yeah.
Right? Anyways, the behavior from the left and from the right has to be
like
the same.
The circle, I liked it better. When you did that one, I started.
Because the circle is a friendlier
Yeah.
picture. It's easier to look at.
Yeah.
Right? When you have an arbitrary graph or any function, then it gets weird to look at, but the idea is exactly the same. The point is, if you have 2 points, you know how to find the slope. Just let's get close to the point that we're interested in, and then the observation is that those lines get closer and closer to the tangent line. So you take the limit, and that's going to take you the slope of this. Why do we only care about the slope? Because remember, we want the equation of the line. But what do you need for the equation? You need a point and the slope. The point we have, we just need the slope. And that's why the whole focus is on the slope. Okay? So, and then, you know, if you remember back from college algebra, we do have a way of computing, of keeping track of all the slope of the secant lines. That's what we call the average rate of change of the function from one point to the other. Okay? And that's where this little formula comes from. So this is the average rate of change from A to A plus H. Right? So what we do is we just take the limit of this expression as H approaches 0, because H approaching 0 means that these X values over here, which correspond to the X values of these points, they're getting closer and closer to it. Right? We're just making this tiny distance, this distance very, very small. And that's how we define the slope of the tangent line. The limit as H approaches 0 of this difference quotient. Okay? From A to A plus H. Now, this is the definition of the slope of a tangent line, and then of course this is a limit. This limit may or may not exist. If it exists, then we say the function has a tangent line and the slope is M. There are different names that M has. We call M the slope of the tangent line. It's also the slope of the function at the point A. It's also called the derivative of the function at the point A. It's also called the rate of change of the function at A. All of those names, they are all the same, okay? And all of that is written in this little paragraph here. And then we have this special notation that we like to write f prime of A, and this is just another way of writing n, okay? And the idea was, okay, now this is good, but what if I'm interested now in another point? Do I really need to compute this all over again and do this every single time that I change my point? So the idea is, let's try to turn this into a function. So if I want to be able to change this A as much as I want, so let's put an x in here, okay? You put an x in here, and then you're going to obtain a function. When you put an x, that's what we really call the difference quotient of f that you used to compute back in college algebra, and the limit is what we call the derivative of the function. Okay, so definition is down here. Okay, so we define the derivative of a function as the limit as h approaches 0 of the difference quotient. Okay, the point is that this is going to be a function of x, and what are the outputs of this function? The values of this function are all possible slopes of all tangent lines that you can get on the graph. Okay, of course, to get an output, you need a number. So give me a point, plug it in, and you're gonna get the slope of that particular tangent line. Change the number, plug it in, you get the other slope, and so on. Okay. So typically, if you have a function and you have several questions, and then each question asks you for the slope at different points, what you should do is compute this first, the derivative, and then you just plug in whatever you have, and you don't have to compute the limit every single time. Okay. And since I'm here, we have different notations for the derivative. We typically use this one, the prime notation. But sometimes this notation is used, this is called the Leibniz notation, okay? This is gonna make more sense later on when we talk about higher order derivatives. And I guess you will really appreciate this when you get to calculus 3, those of you that have to take calculus 3, okay? Anyways, this means exactly the same thing. You can think of this as being an operator, and what this is telling you is, let's take the derivative of this function with respect of this variable. Derivative with respect of x of y, derivative with respect of x of f. Right now, this is not too meaningful because we only have one variable, but you may have a function of 2 or more variables. So it's important to specify with respect to what you're taking derivative. Okay? But that's calculus 3. You're going to do that in calculus 3. You're going to analyze functions of more than one variable in calculus 3. Okay. Anyways, this is just notation, okay? We primarily are going to be using this one, but keep in mind that you may see this from time to time. And I may write this from time to time just so you get used to it. And, you know, the point is right now all we have is a definition. So the idea is that today we're going to do a couple more examples. We're going to analyze this concept a little bit more, see its relationship with continuity, and then we're going to start moving towards some formulas. Because every time that you want to find derivative, for example, something as simple as this function, x squared plus 1, you don't want to be dealing with a limit like this. Imagine that I would have said x to the 100 plus 1. Are you really going to do x plus h to the 100? You're going to be there forever. So we want to have some nice formulas that allow us to compute this in split of a second. Okay? And that's the kind of stuff that we're going to start doing today. But before we get there, we need to understand what we're doing. Otherwise, you're just mechanically using formulas and you have no idea what's happening. Okay? So, okay, and here we did some examples. Here I made a little observation that there will be some important points in the graph that we will be interested in. And in particular are those points at which we have horizontal tangent line. Okay? In the next chapter, when we start looking at application, you're going to see why. And you can probably guess what's happening here. Notice that this point, this vertex of the parabola, is an important point. What's special about this point that no other point the graph has, other than it has horizontal tangent line?
Why is it?
Okay. What else?
It's the minimum.
Okay, but that's, we call it vertex because it's a parabola, but it could be some another function. What else this point has that no other point has?
What's the lowest point?
It's the lowest point. It's a minimum value of the function. In this case, let's call it relative minimum because the function could be doing all stuff to the right. But around this point, this is the lowest. And notice that it has an important property. The tangent line at that point is horizontal. Okay? And notice that if you think about it, that's also what happens in most of the cases. For example, this is a cube, right? This is a degree 3 polynomial. And there are two relative extrema here. There is a relative maximum and there is a relative minimum. Do you see what they are? Do you know what I mean by relative? It's in a little piece of the graph, it's either the highest or the lowest point. Hopefully you agree. I'm talking about this guy and this guy down here, right? If you focus on a piece of the graph, that's the largest point. If you focus on a piece of the graph, that's the lowest point. What do they have? What happens at those points if you look at the tangent line?
Change direction.
But what happens to the tangent line at those points? If I were to draw tangent lines, horizontal tangent lines. This would be a theorem. And we will be interested in this point. It's a very important point. It's at the relative extrema. Okay. So if you want to know when the function has a maximum or a minimum, what should you look at? You should look at those points at which the derivative, at which we have a horizontal tangent line. So you need to be able to spot horizontal tangent lines. And remember, you need to do that from the formula, not from the graph. You have the graph, you already have everything. The whole point is we can graph later. Okay. So how do we find these points? This is the clue. The derivative, we need to have a horizontal tangent line at those points. What does it mean to have a horizontal line? It means that the slope has to be 0. So if you want to locate these points, what do you need to do? You need to find where the derivative is equal to 0. We're going to be doing this a lot in the next chapter. Finding points at which the derivative equals 0, because those are the points at which you could have a maximum or a minimum. I'm saying cool because it doesn't have to be. If you think about the cubic function, right? Y equal x cubed. Let's look at this point here. If you get close to, with secant lines using the construction that we were doing before, you will see that actually the tangent line, quotation mark, is this one. It looks like this. Okay? Of course, this is not a conventional tangent line. You always think about tangent line and just touching. Here is kind of crossing the graph. Okay? But nevertheless, it's only at one point. But if you get close to this point from either side, this is the kind of line that you approach. Okay? And in this case, this is neither a maximum nor a minimum. Do you understand this? So it doesn't mean that if you have a horizontal tangent line, then it has to be a maximum or a minimum. No. But if you have a maximum or minimum, you're going to have this other situation. Okay? And there is another one that we discussed today, which is this one. I will erase all of this, but this is a good introduction to the ideas that we're going to talk about. Let's think about the absolute value function. Put it upside down. Let me put the absolute value. And again, this point here is a minimum, right? So, question: what's the tangent line at this point for this graph? Can you make sense of the tangent line? And remember, the way that we make sense of it was by taking this limit. Took a point and we got close to our point, and then we were looking at the secant lines and seeing that they approach a particular line. And we do that here. Let's see. Let's look at the left of the point. If I pick a point here and then I go towards the red point, what sort of line am I going to get all the time? What secant line do I get all the time? I always get this one. This doesn't change. I mean, you are already on a line, right? There's no curve here. If I do it on the other side, and I go towards this point, what sort of line do I get? I get this other line. Yes? So what's happening? When you do it from the left or from the right, from either side, what's going on is that from the left we're getting one line, so we get one slope. In this case, a negative slope, right? The blue slope. And from the right we get the slope of the green line, which is a positive slope. So what do you think is happening here? Do we have a slope at this point? We don't, because we have different values. The limit doesn't exist. If you look at the side limits, you're going to get two different numbers. A negative number because of the blue and a positive number because of the green. You understand this? So there is no notion of tangent line at this point, because you have two possibilities actually, the blue and the green. So there is not a unique tangent line. And therefore, you also need to consider these kind of cases when you're looking for extreme values. Because if you only look at horizontal tangent lines, you will be then skipping this case. And you still want to find this. So the way that we're going to say is that the places where the function could have minimum or maximums are points at which the function has horizontal tangent lines or is not defined, where the tangent line is not defined. The derivative doesn't exist. Okay? Again, this is one of the first theorems that we're going to see in chapter 3. That's why it's important to understand this geometric construction. Otherwise, you may have some issues later on to assimilate the concepts that I'm explaining now. Okay. So again, we're gonna touch on this later today when we talk about differentiability. And this is a classical example of a function that's not differentiable at a point. When you have a corner, when you have a peak like this, whenever you have a graph, if a peak like this is formed, then what's happening is that when you get close to this point, from one side you're gonna have this sort of tangent line, and from the other side you have a different one. So there is not a uniform one. Okay? If the function does, a nice turn like that, then it's different because when you get close to it, it goes towards this line, and from this side, the same thing will happen. Okay? So peaks are a problem for resistance of tangent lines. And of course, gaps and stuff like that are also a problem. Okay? So keep that in mind because you have some questions in the homework that deal with this. But we're gonna formalize that later today. Okay, so I guess the moral of this discussion is it's very important to know when the derivative is zero. Okay? And that was the remark that I was making here. To understand that for that function, because the derivative is 2x, when x is equal to 0, then the derivative is 0. So that means at the point 0, whatever the function is, in this case the function was x squared plus 1. So at the point 0, 1, we have a horizontal tangent line, as the picture shows. Okay? So that's an important question to be able to find. The points at which the function has a horizontal tangent line. Okay. Any questions on this? All right. So I did some examples. Let's do 2 more, and then let's talk about this relationship. Is there a relationship between differentiability and continuity? We'll define what differentiability is and all of that. All right, but before we do that, let me just remind you of the definition here. So recall, if f is a function, then f prime of x, this is the limit as h approaches 0 of f of x plus h minus f of x over h is the derivative. Is the derivative of f. And then if f prime of a exists, what I mean is if we replace x by a in here, right? So that will be f prime of a. If that exists, that limit exists, then that number represents the slope of the tangent line. It represents the slope of the tangent line to f at the point a comma f of a. Okay, so that's the geometric meaning of what we are computing. So let's do 2 examples. Let's see. The first one is find the derivative of, and let's see, let's do square root of 2x plus 1. And then second, find all points on which f has a horizontal tangent line. For the function f of x equals, so let's see, let's do 2x cubed plus x squared minus 2x minus 1. Okay. All right, so go ahead and try these problems. Anybody has an answer for number 1? by the way, among the rules that we're gonna learn, you're gonna be able to do this derivative pretty fast, okay? It means that we don't know anything now, all we know is the definition, so we have to suffer with the limit, okay? But the idea here is I want to give enough motivation so that then you pay attention to the rules. Otherwise, you have to be taking limit all the time, and it can get pretty tricky, okay, depending on the function. Anyways, this is something that can be done. Anybody has an answer for this one? Yes, what did you get?
1 over the square root of 2x plus 1.
Very good. Very good. All right, so let's see. So we have f of x, which is square root of 2x plus 1. Okay? So let's start with the definition. So our job is to take the derivative. So what's the definition? That's the limit as h approaches 0 of f of x plus h minus f of x over h. So the first thing that you have to be able to do is to actually evaluate this correctly. In other words, plug in correctly into the function. So I want you to tell me what I should write next. So limit as h approaches 0 of what? What goes in the top? Who can tell me? First term, what is it?
The square root of 2x plus 1 plus h.
You mean this? Like that?
Minus square root of 2x plus 1.
Okay, wait. No, that's not what it is. So what does this mean?
The h goes outside.
No. So what does this mean? Let's see, let me ask you an easier question. If I ask you to do this, what do you do? What do you do? I don't understand what you're saying, so say it loud.
Plug in the 1.
What does it mean to plug in?
Oh, you change the where it says that the letter of where f equals x, instead of the x, you put the 1 there instead.
Good. That's what it means to plug in. You replace x by 1, right?
So
And therefore, in the top, what do?
you change the x to everywhere it says x into a 1.
No, okay. Now here. Use the same idea.
Move the x and from fx, f1 plus h. I can't really see the here.
This is an x plus h. There's no 1 here.
No, you change the x into a 1.
Okay, for this one, yes. Now use the same idea for the top. What do you do when you see this? Okay, let me erase this. Okay, first of all, everybody understand that if you want to do this, what you do is, when you see an x, you put a 1. Yes? Okay, let me erase that. So there's no confusion now. Who can tell me what do we do in the yellow?
2 times x plus h inside, because that's where the x is, plus 1 in the root.
So replace x by x plus h. That's what it means to plug in. What this is telling you is, go to the function, and every place that you see an x, you're going to write x plus h instead. Do you understand that that's not what happened here? Do you understand that this is different? What I just said. Okay. So what would be the case? Square root of 2. Okay, I see an x. I'm supposed to write in there x plus h. And then plus 1. So my advice to you is, whenever you're going to plug in something to a function, just write the same formula that you see, and when you see the variable, just put parentheses. And just finish writing the formula for parentheses, and then fill in the parentheses. You know, if this gives you trouble, just write this. And then inside the parentheses, you put whatever you need to put. What do you put here? Well, whatever is being written here. Do you understand this? Which in this case, for example, it would be x plus h. Okay, so that's the first term. Then minus, what's the second term?
Root of 2x plus 1.
Square root of 2x plus 1, the function itself, right? And then over h. Are we okay with this? All right, so that's what we have here. Now again, notice that if you want to take the limit, you're gonna get 0 over 0. Does everybody understand this? If I I take the limit, I get 0, 0. So let's begin by simplifying this as much as we can before we do something. So inside the radical on top, we can distribute the 2, so we get 2x plus 2h plus 1 minus square root of 2x plus 1 over h. Okay, so again, this limit is 0 over 0, so we need to do something. What's the technique in this case? We multiply by the conjugate. The conjugate of what? Of the top, right? Which is the same thing, but with a plus instead of a minus. So let's do that. So I'm going to multiply top and bottom by the conjugate of the top. That's 2x plus 2h plus 1 plus square root of 2x plus 1. So we do that in the top and the bottom. Why are we doing this? Because then on top we're going to have a difference of squares, right? Because we have a product of conjugates. So that would be, when you multiply the top, that would be the first guy squared, killing this radical, minus the second guy squared, killing that radical. Yes? So limit as h approaches 0. Then the first one is going to be 2x plus 2h plus 1, because when you do the square, the radical is gone. Minus, I'm going to put parentheses because this minus is going to affect the whatever is left. Then when you square the second term, the radical is gone. So we get 2x plus 1. And then over h times all of that. I'm not going to distribute because remember, our job is to cancel that h. This h down here is responsible for the 0 in the denominator. We want to get rid of that so that we can compute the limit. Do you understand so far? Okay, so now let's simplify. So hopefully you see that some nice stuff happens when you distribute this negative. The 2x will be negative, which cancel with this one. The 1 is going to be negative, which cancel with this one. Yes? So this 2x is going to be gone with this one, and the 1 here is going to be gone with this one. Does everybody see this? So what survives on top? What do you mean 0? 2h, right? So we have a 2h on top, and then in the bottom we have this quantity. And now we can happily simplify the h, right? And notice that the problem is gone now. We no longer will have a 0 on top because now we only have a 2. So when you take the limit, you're not going to get 0. And the responsible for the 0 in the bottom is gone now. Yes? So when you take the limit, what do we get? What do we get in the limit? That's the quotient, limit of the top divided by limit of the bottom. What's the limit of the top? What's the limit of the top?
0.
Why 0?
2.
It's 2. We have a constant 2, right? I just said the 0 is gone. Right? We no longer have the 0 anymore. We simplify this h, so now there is only a 2 left over. You take the limit, you get 2. You get 2 in the top, then what do you get in the bottom? Well, h approaches 0, so it's only this term right here that goes to 0. So this little guy goes to 0 in the limit, so the rest stays the same. So 2x plus 1 plus square root of 2x plus 1. That's the same quantity, so we can combine it. And then notice how 2's cancel out, and so we end up with 1 over square root of 2x plus 1, as your classmate said. Any questions on this calculation? Do you understand what we did? All you do is make sure that you can plug in x plus h successfully, and then multiply by the conjugate. That's all. And then you simplify, and you're done. When you take the limit, remember, taking the limit is just plugging in. After you simplify, you just plug in h equals 0. And then simplify whatever is left. Yes?
For the denominator,
Uh-huh.
to h, what do you do to get rid of it? On the
We we took the limit. You see, there's no word limit anymore. So what does it mean to do limit as h approaches 0? Just plug in h equals 0. So this guy goes to 0, right? If I put 0 here, this becomes 0. So, okay, if you want, this would be 2x plus 0 plus 1. Right? Because it's that little guy, when we took the limit, this one went to 0. Yes? And the rest stays like that because there's no more h anywhere. You okay with this? All right, so that means that f prime of x equals 1 over the square root of 2x plus 1. Or alternatively, we can write the derivative with respect of x of the square root of 2x plus 1 equals 1 over square root of 2x plus 1. This is just the same thing but different notation. Okay? This one's nice because it is actually telling you the derivative of what function you're taking. If I write this, you can wonder what is f. Then you have to scroll up to see what f was. If I write this, then you see everything. Okay? By the way, that will be the kind of game that we're going to play at the end of the semester. We're going to be doing this backwards. The game will be, I give you this, and your job is to tell me f. Okay? That's called integration or anti-differentiation. It's just doing this backwards. So first you need to know how to take derivatives. You need to understand the rules once we discuss the rules, because then we're going to do it backwards. Okay? And that's what you're going to be doing half of calculus 2 if you will. More advanced integrals. Okay? All right. Okay. Questions? All right. How about the next one? Did you get a chance of working on this? All right. So let's do it together. Otherwise, the whole class is going to be gone if we wait too long. Okay? But the point is that the idea is the same. The reason why we are doing this, once again, because I want you to, it may sound bad, but I want you to suffer a little bit first, so that then you appreciate the rules. Okay? Because usually students complain, oh, but there are a lot of rules. Okay, don't learn them, then take the limit all the time. It's always the same limit. The point is that the limits get very complicated when the function changes. So every time that we have a different type of function, you're going to have a different type of rule. Okay? So there will be a bunch of differentiation rules. But the good thing is you will be able to look at this and tell me the answer in less than 30 seconds. Okay? Now we're going to suffer a little bit with the limit. Right? And also the fraction. Okay, anyways, let's do this problem. So why am I talking about derivative? There's no word derivative. Do you see a word derivative in number 2? So when you read this, you need to understand that you need to compute derivative. Okay? So let's read the problem to hopefully understand this. So find all points at which f has a horizontal line. Okay, I should say horizontal tangent line. Okay? So find all points at which f has a horizontal tangent line for this function. Okay? So you have a graph, and want to know what are the points on this graph at which we have horizontal tangent line. So we don't even have a picture, so if you have a picture, you could look at it and probably tell. But how do we do this? Yes?
You get the derivative and then 2 equals 0 and solve.
And why do you get the derivative?
Because it's the tangent line.
Very good. So this word is the one that tells you that you need to be looking at the derivative. Because remember, derivative is related to tangent lines. Yes? What about derivative on tangent line? What does the derivative tell you for a tangent line? The slope, right? And if you want to find tangent line, then you need to know the slope, right? So you need to find the derivative so you can figure out the slope of those tangent lines. Now, what else? Is that enough? If you take the derivative, you're going to get all possible slopes of all possible tangent lines. We don't want whatever tangent line. We want special ones. What do we want? We want those that are horizontal. What does it mean for a line to be horizontal? The slope is 0. So the word horizontal tells you, so this word tells you that the slope must be 0. This word over here tells you that you need to look at derivative. Yes? So like your classmate said, when you put all of these words together, what's the essence of this problem? Figure out when the derivative is equal to 0. Do you understand this? So I'm not going to tell you, find when the derivative is 0. I'll tell you something like this. Because that's what it means. Okay? So to solve this problem, the job is find the derivative of the function, whatever it is, and then set it equal to 0 and solve the equation. And the solutions to that equation will be the points at which we have horizontal tangent. Okay? So let's do it. All right. So for number 2, let me put the function here. So the function was 2x cubed plus x squared minus 2x minus 1. 2x cubed plus x squared minus 2x minus 1. Make sure. Yes. Okay, so now that we have this, let's begin the problem. So first, you know that we need the derivative, right? So first, we need the derivative. So let me write here. The plan is find the derivative. So find f prime. That's step number 1. And what's step number 2? Plug in 0. If you plug in 0, you are finding the derivative at 0. Find whatever makes the derivative equal to 0, right? In other words, solve this equation. Do you understand this? This is the plan. That's how you answer this type of question. Find the derivative and then to solve this equation. That's how you find horizontal tangent lines. Okay. So for the derivative, you know, right now, unfortunately, we just have the limit. Oops, what am I writing? So that's f of x plus h minus f of x over h. It's going to be painful. Painful in the sense that it's going to be long, but as I said, today is the only day that we're doing it. And the days that you spend doing the homework for this topic. After that, then you're not doing this anymore, at least not so often. Okay, so I'm going to go ahead and plug in x plus h. So I'm going to write now this term. Okay, I'm going to plug in x plus h. What does that mean? I have to go to my formula. Every place that I see an x, I replace it by x plus h. So, as I suggested, just, put parentheses. Write down your formula, and whatever you see the x, just put parentheses. And then inside the parentheses, you put the x plus h. Are we okay with this? All right, so as the first guy, then minus. The reason why I'm opening parentheses now is because I'm going to write f of x, but because f of x is a polynomial, this minus here is going to affect all of that when you distribute. Okay? If you don't put parentheses, then you're going to get the wrong thing. So let me put it here over here as well. This first big parenthesis is f of x plus h. Now the next one is just f of x. And then over h. All right, so I'm just gonna keep on writing this limit, but now what we're just doing now is algebra. Now our job is to expand all of this, combine like 10, and simplify as much as we can. Okay, so here we have a cubic, so let's do that one. So that one is x cubed plus 3x squared h plus 3x h squared plus h cubed. Okay, if you don't remember this, unfortunately, then what you need to do is x plus h times x plus h times x plus h, right? Multiply it 3 times. Okay, so that's that. I mentioned Pascal triangle some time ago, at the beginning of the semester, I think. No? How to stand binomials? I talk about this, and the way that you can figure out these coefficients is using Pascal triangle. Okay? For example, this is 1, 3, 3, 1. You get that from here. 1, 1, 1, then 1, 2, 1, and then 1, 3, 3, 1. Those are the coefficients that you put in there. Okay, so this will help you, if you, for example, if you need to do to the fourth power, it will be the next row. What's the next row of the triangle? 1, 4, 6. You have to add, you see, so you start with a 1, then you add 1 plus 3, 4, 3 plus 3, 6. And the next one, 3 plus 1 is 4, and then 1. You always have 1 in the outside. So those will be the coefficients of x plus h to the 4. Okay? And the way you do it is, remember, there are going to be 5 terms, because there are 5 coefficients, and the sum of the degrees always has to be 4. And you start by starting with 4 on x, and then you decrease 1 here and increase 1 for h. So the terms are x to the 4, and the next one is x cubed, and then an h, then x squared, then an h squared, x h cubed, and then an h to the 4. Those are the terms, and then you put the coefficients. So that's a 1, then a 4, then a 6, then a 4, and a 1. And that's how you can expand that without having to multiply. Okay? But again, you're not going to have to deal with this too long, so don't worry too much. But it's helpful to know this. All right. So let's do the next one, which is the square. So that's x squared plus 2xh plus h squared. I don't need to put parentheses because we have a plus. And then the next one is negative 2x minus 2h. And then minus 1. Okay. Then, okay, let me stick it in here. So negative 2x cubed minus x squared plus 2x plus 1. I just distributed the negative in the last parenthesis. All of this over h. Now, technically now in the next step, I should distribute this and then start canceling stuff. But we're big guys, so we can do that now. Okay? So let's focus here. But let's see. Here is a negative 2x cubed, right? And over here, there will be a positive 2x cubed. Do you see that? So this guy is going with this one after I distribute the 2. Is that clear? Okay, good. What else is gone? So let's see. I see a negative 1 over there. So this negative 1 is going with this positive 1. So we can get rid of that. X squared here, and there is a negative x squared over there. So this guy over here is going with this one. Okay, the 2x. There is a negative 2x over here. It's going with this positive 2x. Yes, all of that cancels. Okay. Is there anything else? 2xh. Oh, that's fine. So not. I don't think nothing else cancelled. If something else cancelled, then we will figure it out in the next line. But at least we got rid of some stuff. So let's see. So after I distribute the 2, I'm going to have 6 x squared times h plus 6x h squared plus 2h cubed, then plus 2xh plus h squared minus 2h. Everything at the end was cancelled over h. Everybody okay? This is what survived in the top after doing all the cancellations. Now, again, you don't take the limit yet because we're still going to have 0 over 0. But here is the good news. We want to get rid of this h in the bottom, and in the top, everything has an h. So you can factor out the h and then it will cancel. Or just divide everybody by h, however you want to look at it. Okay? So the point is that if you divide everybody by h, what do we get? Who can tell me what expression do we get after simplifying? It's easy. Just divide by h every term. What do we get?
Oh,
6x squared plus
6x squared
plus 6xh, right? this h cancel with one of these ones,
Oh.
another one survives. Yes?
Plus 2h.
Plus 2h squared.
All right. 2x.
Plus 2x.
Plus h.
Plus h.
Minus 2.
Minus 2. Good. Everybody understand what happened here? All I did was divide everything by h. That's what this is saying, right? You have a fraction over h. You can split this into a bunch of little fractions, and all of them will be over h, so you simplify. Yes? Or, alternatively, you can factor the top, the h, and then cancel it with this. If you factor the top, the 1h, this is what remains. Everybody okay with this? Okay, now we're free to take the limit. Let's take the limit. Everything that has an h is gone, right? When we take the limit, this is gone, this is gone, this is gone. So it goes to 0, it goes to 0, it goes to 0. And what's the answer? 6x squared plus 2x minus 2. So the derivative of the function is this. As I said before, once you know the rules, you're going to be able to look at this and say that the answer is 6x squared plus 2x minus 2. Very quick. Okay? But we need to learn the rules first. Anyways, that's what we have so far for the derivative. Any questions on the computation? Okay, are we done? This was just step 1. What's step 2 now? So set it equal to 0 and solve, right? So now we want to figure out when the derivative equals 0. In other words, 6x squared plus 2x minus 2 equals to 0. We want to solve this equation, okay? So let's go for it. So this is a quadratic equation. If things come to worse, if we cannot factor, then we just use quadratic formula, okay? So not really a problem here. So let's go ahead and let's divide everything by 2, just to make the number smaller, because everything is even here. I'm going to divide everything by 2. So we get 3x squared plus x minus 1. And let's see, can we factor this nicely? So we need to find two numbers whose product is negative 3 and the sum is positive 1. Can we find such a number? No, right? Product negative 3, sum 3 is prime, so there'll be 3 and 1. One of them negative, there's no way you can get 1. You either get a 2, 3 minus 1, a 2, or a negative 2, 1 minus 3. So there's no way to get positive 1. So I'm going to use quadratic formula. So I'm going to compute the discriminant. So recall the quadratic formula. Who remembers the quadratic formula? Do you know what I'm talking about when I say quadratic formula? Okay, what is it?
Negative b.
Negative b.
Those are minus square root of b squared minus 4ac. Or over 218.
Over 2. Good. So when I do this, whenever I need to do it, what I like to do is I like to compute this guy first. This has a name. It's called the discriminant. It's called the stuff inside the square root. It's called the discriminant. B squared minus 4ac. And why is it helpful to compute this first? Because you can see right here, if this is a negative number, when you compute it, what's going to happen? What type of solutions do you get? If you have a negative inside square root, you're going to get an imaginary number here, so you get complex solutions. And that's not what we're interested in. We're only looking at real solutions. Yes? Because we are looking for points on the function, so no complex numbers here. So it's a good idea to compute this first. And if you get a negative number, you already know that there are no solutions, no real solutions, so you're not going to find any horizontal tangent line. If you get 0, then you know there will be only one solution, namely negative b over 2a, whatever those are. And if you get a positive number, then you know you will get two solutions, one with the plus and one with the minus. Do you understand this? So it's a good idea to always compute that one first. I like to call it D for discriminant. That's typically how we call it. So let's compute that. Everybody knows what A, B, and C are, right? Okay, so it's going to be 1 squared minus 4 times 3 times negative 1. Good news, we get a positive number here. So that's 1 plus 12, so that's 13. So it's positive, so that means we're going to have two real solutions. And what are they? So x1, that's going to be negative 1 plus the square root of 13. The good thing is that we already computed that, so you don't have to put the big formula. You just put the answer in there. Okay? You can also use that as a little shortcut. Over 2 times 3. And the other solution is negative 1 minus square root of 13 over 2 times 3. So that's square root of 13 minus 1 over 6. And this one is negative 1 minus square root of 13 over 6. They happen to be irrational numbers, but it's what it is. Okay? These are numbers. So, okay, so these two numbers, these are the solutions to the equation derivative equal to 0. So that means that for this, at these x values, our function is going to have a horizontal tangent line. If you want to know the actual point on the graph, what you need to do, this is the x. You have to plug into the actual function to get the y. Okay? I'm not going to do that because it's a pain. Anyways, as long as you know the x, that's you know you can find the y by just plugging in. Okay? So f has 2 horizontal tangent lines. And that happens at x equals square root of 13 minus 1 over 6, and x equals negative 1 minus square root of 13 over 6. Okay, questions? Any questions? For example, again, this is now a little review from pre-calc. The original function was, what was the function? 2x cubed plus x squared minus 2x minus 1. Later, in chapter 3, what we're going to be doing is I'm going to be giving you functions like this, and then I'll ask you to graph it. So, I mean, this is what you used to do in pre-calculus polynomials, so that's nothing new. The good thing is that now you can do a more accurate graph, because in pre-calculus you couldn't tell, you know that the function is turning, but where is it turning? What's that point at which it turns? When is that you have your maximum? When is that you have your minimum? Now we know. Now you can find those points. Okay? So let's produce a more accurate graph. The way I created this function is so that we could factor, because you know a whole different story is try to factor this to find the zeros and so on. But here we can't. Let's do it is by grouping. So I'm gonna group first 2 and the last 2. In the first pair, I'm gonna factor out an x squared, so we get 2x plus 1. And in the second pair, I just factor out the negative, and we get 2x plus 1. So finally, and this becomes 2x plus 1 times x squared minus 1. And so this is 2x plus 1, and then x plus 1 is minus 1. So this function equals this, but why is this helpful? Because now you see the zeros, right? What are the zeros of the function? What are the zeros?
1 and
Negative 1 half.
And negative 1 half, right? There are 3 zeros. It's just set each factor equal to 0. Negative 1 half, negative 1, positive 1. So that means, let's say, this is negative 1, over here is negative 1 half, and over here is positive 1. So our function is going to go through these 3 points, right? Those are the zeros of the function. And now to graph this, we just need to look at the end behavior, which is given by the leading term, because it's a cubic, right? And the coefficient is 2. Then that means it's going to start down here, and it's going to finish. So it starts in quadrant 3 and finishes up here in quadrant 1. Yes? And the multiplicity is 1, so that means we're not going to touch at any point. We need to cross all the time, right? So it's kind of, now hopefully you see how the graph looks. It looks like this. You know, in pre-calculus you will say, oh, and then somewhere in here we need to turn back down because you have to go through this guy. And then somewhere in here we need to turn back up because we need to go through 1, right? Well, now we can be more precise. We can say, when is this somewhere and when is this somewhere? Why? Because these are the points at which we have horizontal tangent lines, right? So this point right here, which is the one that has a horizontal tangent line, now we can tell what is the x value for that point. Who can tell me what is this x value? What is it? Which one is this one?
-1 minus the square root of 13 over 6.
That one right there, because that's the one that's negative, right? That number is negative. The top is negative and the bottom is positive. And this one is positive because square root of 13 is more than 1. So this one, the positive guy, is the one that corresponds to this one over here. Okay? So now we know this point is -1 minus square root of 13 over 6. And then this other point, I wish, let's see, we can do this a little bit better. So that is a negative, the y-intercept is -1. So let me do the picture a little bit nicer. Let's say -1 is over here. So we need to go through this point. And then this other point down here, which is the one that which we have a horizontal tangent line as well. This x value, we also know what it is square root of 13 minus 1 over 6. This we couldn't do it back in free calculus. We knew this was the general shape. Somewhere it has to turn back down, somewhere it has to turn back up. But what's this somewhere? Well, now we know exactly. There. Okay? That's why this is helpful. Among other things that you're going to see soon. Okay, questions? Again, you don't have to do this. This is basically the kind of stuff that you're going to be doing later, okay, in chapter 3. Right now, the question was to just find these points. Okay, but now you know why we're doing this, because now we know exactly where the turning happens. Remember at the beginning I told you, all of this is so that we can understand functions. We want to study functions. I give you the formula. Study the function. Tell me everything that you can about this function. With the hope that ultimately we can produce a picture. That's the upshot here. Okay. Questions? All right. So this seems weird. Fix it. Still weird, but it's better than before. Okay. So I was those two. Okay. Now let's actually talk about this. Differentiability versus continuity. So hopefully now you have more or less an idea of what differentiability is. So the question is there a relationship between differentiability and continuity? Remember, continuity is that you can draw the picture without lifting your pencil. No holes, no gaps, nothing weird happening in the function. Okay? Differentiability means that the derivative exists. You can make sense of tangent line. Okay? Is there a relationship? So if the function is continuous, does that mean that it has to be differentiable at a point? Or the other way around. If the function is differentiable, does that mean that it has to be continuous? Okay, this is the property that this is the question that we want to explore now. So first, let me give you a definition. We say a function is differentiable at a point if the derivative exists at that point. Okay. So let y equal f of x be a function. Okay. Then first, f is differentiable at x equal a if f prime of a, remember that's the limit as h approaches 0 of f of a plus h minus f of a over h, if f prime of a exists. In other words, if the derivative exists. Okay, that's what it means to be differentiable at a. And then immediately I can tell you that f is differentiable at an open interval if it's differentiable at every point inside that interval. Differentiable on the open interval AB if it is differentiable at every point inside AB. Okay? In other words, if you can make sense of tangent line at every single point, inside this open interval. I want to give you now the definition for a closed interval, but for that, I want to revisit this. This is the formal definition that we have for derivative because this is the one that generalizes nicer, it generalizes in a nice way to a function. Just replace a by x, and then you get the derivative function. But for actual computations, if you're just interested in derivative at one point, this is not fun. The fact that I need to plug in this a plus h is ugly. I don't like it. There's another way that we can rewrite this. So there is an alternative way for writing this limit at a point. Not with x, but when it's at a point, there is another way of writing this. And it's actually easier for computation. So let me say here, note. This is the alternative form. Alternative form for the derivative. At x equal a. And so you see that it's exactly the same thing. It just looks different and therefore makes it easier to compute. Let me show you what's happening here. So far what we have is here is our function y equal f of x. Let's say here is a. And remember, we're trying to make sense of this tangent line. So the idea is to take a point away from it, and then let's call this h. Probably should have done it from the right, but I want you to understand that in this case, h will be negative, a negative quantity because we are approaching from the left, okay? And you approach 0. But I'm going to call this a plus h. Let me do it from the right to avoid confusion. So pick a point here. This is a. Then this distance here, let's call it h, so that's our a plus h, okay? So remember, really what we're doing when you take the limit is we look at this secant line, the blue one, which is the line joining these 2 points. You look at the slope of this, that's what this expression is, f of a plus h, that's y2 minus y1 over x2 minus x1. When you subtract these two, it's the distance, which is h. That's the slope of the blue line. And then our job is to make h approach 0, right? That's how we're defining f prime of a. Let's change names. Instead of calling this a plus h, I'm going to call it x. Let's call this one x. That's the only change that I'm going to make. And of course, if I call this x, then what is h? If I call this x, then h, remember, h represents this distance. Then h would be replaced by x minus a. Do you understand this? If this point is x, this distance here now is this one minus a. Yes? That's a little piece. And remember, h represents this piece over here. And if you will, if you want, you have that x equals a plus h, so h is x minus a. Just move the a up. Okay. Now let's go to a formula. So f prime of a is going to be the limit of. So let's see. Instead of f of a plus h, that's just f of x, because I'm calling this guy x minus f of a, and then instead of h, I put x minus a. And now, as you have seen the substitutions, when h approaches 0, that means if h approaches 0, then x approaches a, right? So remember, we're going towards this point. So h approaches 0 means this distance is very close, it's very small. That means this x here is going towards a. If you do it from the right, this picture. If you do it from the left, is the alternative picture, okay? And this right here is nicer for computations than what you see above. Okay? So moral of the story, f prime of a can be calculated as the limit as x approaches a of f of x minus f of a over x minus a. We call this the alternative form of the derivative at x equal a. The reason why we didn't start with this at the beginning is because this is good to define derivative at a point, but this is not something that you can generalize for any point. You cannot make this, turn this into a function, because you don't have a place to put an x. We already have x in here. Okay? Before it was easier, that's why we used the previous form to define derivative in general. But if you want to find derivative at one point, and that's all you care about, this is easier to compute. Okay? For example, if the function is piecewise, we're going to do examples of those soon. At that point at which the function changes formula, this is the version that you want to use. Okay? Because you want to know what side you are. It's pretty easy to see if you are to the right or to the left by just taking right or left limit. In the other one, you need to understand that h approaching 0 from the right means that your function is approaching the point from the right or from the left. So this is more natural, I would say. Okay, so this is the alternative form, and now since we have this, now we can make sense of left derivative and right derivative. You know, the left derivative is this limit from the left, the right derivative is this limit from the right. So when you define differentiability in a closed interval, it means that you have to be differentiable in the open, but then at A, we only care about right differentiability because we only look at the right limit. I don't care what happens to the left. And at B, we have left differentiability. Okay? So, B, F is differentiable on the closed interval AB if first it has to be differentiable on the open. So inside the interval it has to be differentiable. And then second is left differentiable at x equal a and should be right differentiable at x equal a. So i.e. the limit as x approaches a from the right of f of x minus f of a over x minus a exists. That's right differentiability and is left differential at b, i.e. the left limit exists. Okay? So after you check differentiability on a closed interval, make sure that it's differentiable on the open, and then to the left is right differentiable, the left endpoint, and the right endpoint is left differentiable. Okay? Similar to what we did for continuity. We had the notion of left continuous, right continuous. It's the same idea. You just take the corresponding limit, right or left limit. All right. So again, the moral of the story is a function is differentiable if the derivative exists. Okay. So let's do an example. So show that the function absolute value of x minus 1 is not differentiable at x equal 1. Okay? And you're going to see why I'm talking about x equal 1. Any other point, it will be okay. The problem is 1, x equal 1 is an issue here. So to answer this question, what we have to do is verify whether the derivative of 1 exists or not. Okay? And our job is to show that that derivative doesn't exist at x equal 1. And because we don't have any formula here, and because this is piecewise, because remember, absolute value are piecewise functions, even though they don't appear to be, they are. We need to do this by definition. Okay? Okay, so solution. I want to find f prime of 1, and I'm going to use the alternative form. This is the limit as x approaches 1 of f of x minus f of 1 over x minus 1. So that's this formula that we have here with a equals 1. Okay? It's way easier because we don't have to deal with this h, nothing like that. Okay? So when it comes the time to plug in, it's actually pretty straightforward. but this is only valid when you're finding the derivative at a point, not in general, like we're doing here. Okay, so let's see, let's compute. So what happens here? F of x is absolute value of x minus 1. Then f of 1, when you plug in, that's 0. And then that would be x minus 1. So we get limit as x approaches 1 of absolute value of x minus 1 over x minus 1. And at this point, it should be familiar to you. We have done limits like this before. What do we need to do? What do we do here? We need to look at side limits. Why is that? If you try to plug in, you get 0 over 0. Do you realize this? So plugging is not a good option here. So in this case, the idea is let's try to get rid of this absolute value, right? And to get rid of the absolute value, you need to know the sign of what's inside. If this is positive, you know the absolute value. If this is negative, you can remove it, but you need to put a minus in front. Yes? So to be able to know the sign of this, you need to know on what side you are. Are you to the left or to the right of 1? Because depending where x is, that's what you can tell about x minus 1. So that's why your classmate said, if you want to proceed here, we need to look at side limits. Okay? So we need now side limits. All right, so from the right, let's see, what do we know about x here? What do we know about x? X is bigger than 1. And remember, we are interested in x minus 1. So what can we say about x minus 1? It's greater than 0. So that means that in this limit, this quantity is positive. So what can we do to the absolute value? We can just remove it, right? Because the stuff inside is already positive, the absolute value is not doing anything there. So I can just remove it. So what is this limit? This is 1, because remember, you can simplify before you take the limit. Okay? You simplify, and then we get the right limit is equal to 1. You okay with this? All right, the next one. We need to do the left limit. What do we know about x here? X is less than 1. So what does that mean about x minus 1? It's going to be less than 0. Yes? So if the stuff inside the absolute value is negative, what happens if we remove the absolute value? We need to make it positive. How do you make something positive?
Oh. Negative and negative. If negative 1 divided by negative 1 there, it turns into a positive, right?
Okay, no. So you want to get rid of this absolute value. We know that to do it, we need to make the stuff inside positive, right? How do you make something positive? You multiply it by a negative 1, right? You know that something is already negative, you multiply it by negative 1 to make it positive. Do you understand this? So if you remove this absolute value, you can do it, but you have to put a minus in front. Do you understand where this minus is coming from? That's because we are removing the absolute value. We have done this. I don't know why you're looking at this as this is the first time that you see it. We have done this several times. And it was in the exam also. This was in the exam. We have done this in class many times. Okay, and now we simplify. And what are we getting this limit? Negative 1. So the right limit is positive 1, the left limit is positive 1. So these guys are different, right? So what can we say about the actual limit as x approaches 1? So this limit does not exist. In other words, the derivative at 1 does not exist. Do you understand this? That was the point of the question, to show that it's not differential at 1. So prime of 1 does not exist. And and hence f is not differential at x equal 1. Okay? So we can now partially answer, part of the question that we were asking earlier. We wanted to see the relationship between continuity and differentiability. Let's see. Is this function continuous at x equal 1? Why not? What limit? I said continuous. I didn't say differential. This limit is for differentiability. The limit for continuity is just this. Yes? A different story. What's the limit as x approaches 1 of the function? What is this limit as x approaches 1? It's 0. The limit exists of a function. This is a different limit. Do you understand this? This is a different thing that we're doing. Okay? Now I'm asking about continuity. Is this function continuous? You can answer this more quickly. This is a composition. Do you see that this is a composition of two functions? What are the functions that are being composed here? What's the outside function? The absolute value function. Or what's the inside function? X minus 1. What do you know about these two functions by themselves? Are they continuous? The absolute value is continuous, right? You can draw it without lifting your pencil. Nothing wrong with it. X minus 1, that's a line. Also continuous. Composition of two continuous functions is continuous. So the function is continuous everywhere. In particular, it's continuous at 1. Yes? But we just saw that it's not differentiable at 1. So, if a function is continuous, does that mean that it's going to be automatically differentiable? No. Here is a counterexample. Okay? Here is a case in which continuity is fine, but differentiability is not. Okay? So differentiability is a more sort of condition than continuity. A function could be continuous, but fail to be differentiable. Now, the question is, how about the other way? If you know the function is already differential, does that imply continuity? Okay, so let's try to answer that question. And the answer is yes. The other way is okay. So continuity does not imply differentiability immediately, no. But the other way, yes. If you know a function is differential, then it has to be continuous. Okay, so let's discuss that. So let me make a remark here. So note f of x, which is x minus 1, is continuous everywhere. In particular, it is continuous at x equal 1. However, it is not differential at x equal 1. So what we have seen so far is that continuity does not imply differentiability. Okay? So knowing that a function is continuous is not good enough. It doesn't tell you whether it has to be differentiable or not. How about the other way? Let's try to investigate the other way. If you know a function is differentiable, then does that mean that the function is continuous? And the answer is yes. So theorem, the theorem is the other way, that differentiability implies continuity. Okay? So if a function f is differentiable at a point x equal a, then f is continuous at x equal a. Okay? So let's prove this theorem to see why this is the case. So remember, this is an if-then statement. How do you argue if-then statement? The if part is your assumption. That's something that you take for granted. So assuming that f is differentiable at a point, what we need to do now is prove the then part. So we need to prove the last part. We need to argue that given that the function is differentiable, now we need to argue that it must be continuous as well. Okay? But we take this for granted now. So that's how you argue if-then statements. to prove. So assume that f is differential at x equal. So we have differentiability at x equal. So that is, so what does it mean to be differentiable? It means that this limit, it means that f prime of a exists, right? That's what it means to be differentiable. In other words, the limit as x approaches a of f of x minus f of a over x minus a, this limit exists. It equals something. This equals a number that we call it f prime of a, okay? That's what we are assuming. From here, we need to argue, so we need to show, so what do we want? It's good to have what we want. So what do we want? We want to show that f is continuous at x equal a. So to argue this, what do we need to argue? What do we need to argue? There are three things that we need to argue. What are they? In other words, the three items of continuity. That was a question in your exam, right? So what do we need to argue?
The function is defined at x equals a.
Is the function defined? Next.
Does the limit exist?
Does the limit exist?
Is the limit equal to
Does the limit exist? And 3, is the limit the same as a function? Yes? So we want to answer these three questions. And hopefully we want to answer yes to these three questions. You understand this? Okay, so let's see. I claim that number 1 is implicitly answered already. Who can tell me why?
because the tangent line exists.
Exactly. Because the tangent line exists. And also look at this. We're saying that this limit exists, right? This limit has f of a in it, right? So for this limit to exist, the first thing is that you have to be able to make sense of f of a. So the fact that this limit exists, because that's our assumption, that this limit exists, it already implies that the function is in a. And if you think about it geometrically, we're saying there is a tangent line, therefore there is a point to look at. Do you understand this? So the first one is automatically yes, since f prime of a exists. Okay, so that's easy. Now I'm going to answer question 2 and 3. I'm going to answer them together. Okay, and the way I'm going to answer these 2 and 3 together is I will alternatively show instead. So we'll show that the limit as x approaches a of f of x minus f of a equals 0. This is what I'm going to argue. So what are we saying here? When x is very close to a, this function is very close to 0, right? But if this function is very close to 0, that means that f of x is going to be very close to f of a. You understand this? So by doing this, I'm answering 2 questions. I'm answering that the limit of f of x exists because it gets close to something. Why it gets close to? F of a. So I'm answering question number 3 as well. You understand this? So 2 and 3, I'm packing those into this limit. Why? Because this is easy to argue with what we have. Now it's pretty straightforward. So we have limit as x approaches a. So f of x minus f of a. I want to compute this limit. Okay? And my job is to show that this limit is 0. All right, so let's do it. So the idea is, why am I doing this instead? Well, because notice that this is exactly what we have in the top of that limit, right? So now I want to bring that into the picture, so I can do a little trick. X approaches a, but it's not equal to a, remember. So x minus a is actually not equal to 0. Close to 0, but it's not equal to 0 because x is not a. Do you understand this? We're approaching it. So I can divide by x minus a. So what I'm going to do is I'm going to multiply top and bottom by x minus a. Why? Because I want to bring this guy into the mix. Okay? So let's multiply top and bottom by x minus a. Again, you can simplify this, and we get back here. So this equality holds. If this makes sense, then this also makes sense. Do you understand this? And now, let's look at this. We have now a product of two functions. And why I wrote like this? Here's one function, here's another. And as you know, the limit of a product is the product of the limits if each of the limits exists, right? What can we say about this first limit? Does this limit exist? That's exactly our assumption. That's what it means to be differential, right? Because a function is differential, this limit exists. Does this limit exist? Yes, x minus a. There's nothing wrong with that limit. So I can split this as a product of two limits. It's one of the properties that we have. And what is this limit over here? The first one. What is this equal to? We have a name for that. What is it? Yeah, it's written right there. F prime of a, right? The limit equals, oops. The limit equals f prime of a. So this is just f prime of a. That's the derivative. Whatever it is, you don't know, but it's something. It exists. And what's the other limit?
0.
That's 0. Remember, plug in x equal a, right? You get a minus a, which is 0. So this is a number times 0. What is it? That's 0. So we just show that the limit of f of x minus f of a equals 0. So we proved 2 and 3 above. Okay? So condition number 1 for continuity, we automatically get it because if it's differentiable, that means there is a tangent line, so the function is defined at the point. There is a point to draw the tangent line. So 1 is okay, and 2 and 3, we argue at once. Okay? Again, I'm not going to require you to do this course. What you need to know is the result. The result is that differentiability implies continuity. If a function is differential, then it must be continuous, not the other way around. Okay? The function may be continuous but not differentiable. Think always about the absolute value function. Are we okay with this? So differentiability is a stronger condition. That, the class of the functions that are differentiable are nicer than those that are continuous. Because another way that we call a function that's differentiable, we say is smooth. So it no longer, it means that it must be continuous, so no holes, no gaps, nothing weird, but it also has to be smooth, meaning if you're going to turn, you need to do it nicely. You cannot do sharp turn like that and create peaks and weird stuff in the function. Okay? If it's going to turn, it has to do it nicely. It has to be smooth. Because you have to have tangent line everywhere. Okay? So that's what differentiability gives you. Like polynomials are differentiable functions. Because you will be able to find tangent line everywhere. They are smooth functions. Okay? But there are functions like absolute values and so on that are continuous but are not differentiable at certain points. So, mark. A differentiable function is also called smooth. I'm putting this in quotation mark because technically smooth means that because it's differentiable, it has a derivative, the derivative has to be continuous. Okay, when the derivative is continuous, then it's smooth. But let's loosely say smooth. A differentiable function is also called smooth because its graph is both continuous, no holes, no gaps, nothing strange, and smooth. And by smooth, what I mean is no sharp turn. Okay? No sharp turns. In other words, you see a picture like this, and then these points that we're turning over here and over here, those are nice, but this one is not good. Okay? That little peak that we have in there is a point at which the function is not differential. not differential. In other words, it's not smooth there. Do you understand what I mean when I say the word smooth? Okay, so you have questions in the homework that they give you a picture and they ask you to determine points at which the derivative does not exist, where the function is not differential. And you have to see, And let me tell you another one, which is how do you know when you have a vertical tangent line? So the question is, what's the slope of a vertical line? It's undefined. Very good. So the slope of a vertical line is undefined. And how do you know that you have a vertical tangent line? That's when your derivative is undefined, but you have to be careful. Your derivative could be undefined because the side limits are different, in which case typically you are in a situation like this. There's no vertical tangent line here. It's just that you have different derivatives, different slopes at the point. But another way that the derivative could be undefined is if your limit is infinity. Okay? We're going to do an example now with the limit is infinity. And when that happens, then that means that you have a vertical tangent line. Because you think about it, why do we say that the slope is undefined? The slope is a measure of inclination of your line. What's the most inclined line that you can find? Think about it as a mountain, right? Mountain has slope, right? Or a hill has slope. The bigger the slope of the hill, what happens? The harder it is to climb, right? What's the biggest possible slope that you could have? A vertical hill like this, right? So that would be infinity. The slope is infinity. If the slope is a number, then it has a slight little inclination, that then you should be able to do something about it. But if you have a vertical wall, then good luck trying to climb that. Do you understand what I'm saying? So that's the definition of a vertical tangent line. Let me give you an example. Find the derivative at 0 of the square root function. Okay? So I don't want to do the whole computation again. I did this one last time, so I'm going to reuse it. Let me just show you so you see that we're not cheating here. So I did the square root function on Friday, and then we came up with the derivative, which was 1 over 2 square root of x. And this, the technique that you see is the same as the first example that we did today. Multiply top and bottom by the quantity. Okay, I just don't want to repeat the same computation. And notice that the reason why I'm saying at 0, because if you now plug in 0, what's going to happen? You get 1 over 0, right? Does everybody see this? So it's going to be undefined. But let's try to see why is it undefined. Well, because we get a number divided by 0, we know there's a type of infinity. So I'm going to come back and take the limit, but now it's a little bit more meaningful. And since I'm doing this, I'm going to do it with the alternative form. That way I don't have to deal with the h. Okay, so from before, okay, so solution from before, we saw that f prime of x is 1 over 2 square root of x. I encourage you to remember this because this derivative is going to pop up a lot. Okay? Like with capital letters, a lot. So when you see square root, you want to know the derivative is 1 over 2 square root of x. Okay? All right. And the thing is that if you can see immediately here that if we plug in 0, then this is undefined. Okay? So let's try to dig a little bit deeper. What type of undefined do we have? Is an undefined like what we see in the absolute value, right? Because the side limits are different, or is it undefined because something else? Maybe we're getting an infinity. And you should realize that yes, we are getting an infinity because what's going on is undefined because we have a number over something that's approaching 0 in the limit that's going to happen. Okay? But let's see. So to see what type of undefined we're talking about, we should look at the limit, and I'm going to use alternative form. Okay, that's the alternative form that we just discussed. Now I want you to realize that this is not fully correct because what's my f of x? What's f of x? 0 to infinity, right? So there's no graph to look at to the left of 0. Therefore, the limit of x approaches 0, we really should be doing x approaches 0 from the right. You understand this? Because from the left, there is no function. This doesn't make sense from the left. Because x negative, there is no function. So we should technically here be looking at the right limit. Because remember, we are analyzing the square root function. Here it is. Right? As a square root function. So there is no function to the right, to the left of 0. Okay, so let's do this. That's limit as x approaches 0 from the right of the square root of x minus 0, because square root of 0 is 0, over x. So that's limit as x approaches 0 from the right of square root of x over x. This is 0 over 0, and now we can easily simplify this. Remember, x is the same thing as square root of x squared, or square root of x times square root of x. Does everybody see this? So I can cancel the square root of x with one square root of x from here, and there will be another square root of x left over. In other words, this x, you can write it as square root of x times square root of x. Yes? And therefore, I can cancel this with this. So we are left with 1 over square root of x. Or you can write this as x to the 1/2 and then subtract exponent. 1/2 minus 1, that's x to the negative 1/2, and then you can write it like this. That's another way to do it. And now let's take the limit. So we see now 1 on top, 0 in the bottom, right? So it's going to be an infinity. What infinity is it? Is it positive or negative infinity? Positive infinity. Because this guy down here is positive. Yes? So that means it's undefined, yes, but now we know what it is. It's positive infinity. This tells me that at that point what we have is a vertical tangent line. And indeed, very interesting what happens at this point. If we pick another point here, all right, this is a point Q, and if we move towards the red point, what's going to happen to the secant lines? Notice that this line right here, I was taller, but not. So you have the secant line here, then like this, like this, like this, like this, and eventually they get closer and closer to the y-axis. Do you understand this? So the line x equals 0 is a vertical tangent line. Okay? So that means the y-axis, which is this one right here, is a vertical tangent line. So how do you find vertical tangent lines? That's when the derivative gives you infinity. Okay? So, definition. F of x has a vertical tangent line at x equal a if f prime of a, which is the limit as x approaches a of f of x minus f of a over x minus a, or a side limit. I just don't want to write all the possibilities, but it's either the full limit or just a side limit. Okay, for a side limit, give positive infinity or negative infinity. Okay, because it really depends how you're approaching to it. So when you tell the derivative it doesn't exist, but if it doesn't exist because you get infinity, that means that x equal a is actually a vertical tangent line. Okay, it's a different situation as with the absolute value. It didn't exist because there were side limits. It's just that they were different numbers. So you have different slopes, therefore you have a peak. That's a different situation on this one. Okay, questions? Okay. The reason for that, so I guess we will do rules on Wednesday, but let me turn back to the screen here. Just to show you Because there is a little question in the homework. I don't want to make sure that you understand how to do that. For example, here's homework 6. Now you know how to do this. This is just use the definition and then find the question of the tangent line. It's not really a problem. Question number 1. For example, let's see. Let's answer this one. The graph of f is shown below. Estimate and list the value of x where f of x has a horizontal tangent line. What would be the answer here?
-6
So right here, that's 1 point. Yes. And down here is 0 point. Yes. So that's a pretty easy question. So that's -6. Okay. All right. So that's just computing difference quotient. Okay. So let's see this one here. How would you do something like this? So they give you the graph of the function, and then your job is to sketch the graph of the derivative. Remember, the derivative of this is another function. Okay? So it has a picture. Let's sketch the graph here from -4 to 4. You should realize that 0 here is an important point because to the left of 0, at any other point, the function has the same slope, right? Namely, whatever the slope is of this line. And to the right of 0, the function has the same slope, whatever the slope is of this line. Do you understand this? So the derivative here is going to be a piecewise function. And the function is going to be flat, horizontal. Because to the left of 0 is going to be one value all the time for the derivative, whatever the slope is. And to the right of 0 is whatever the slope is. Does that make sense? So, to the left of 0, let's look at this piece of the line. What's the slope? 1. Just do right over wrong, right? So, if you want from here to here, you do 1, 1. Yes? So, that's the constant function 1. So, to the left of 0 is 1. Yes? And then to the right of 0, what's the slope? -1 over 2. It's negative because it's going down, and it's 1 down, so 1 and 2, right? It's not right over wrong, but fall over wrong. You fall 1 and you run 2. Okay? So it's -1/2. So here try to approximate more or less what -1/2 is. It should take. Okay? So that's what's going on here. To graph on the same picture the graph of the derivative. And then there is another one. Now you can do this. This is exactly the same thing that we did earlier today. Okay? This one. If you want, use alternative form. It's going to be easier to compute than using the h. Here, you should use the h, the definition with the h, just because then you have to compute 4 times derivative at different points. So it's easier to find the actual formula for the derivative and then just plug in your numbers. And that's what they're suggesting here. I want to get to the picture. What is it? Oh, for this question, I said a few words at the end of Friday. This is for physics. So when the function that you're analyzing is a position function, it's a function that gives you the position of a particle, the rate of change of that function, so the derivative has a physical meaning. That is velocity. Okay? The instantaneous velocity of a particle is just a derivative of the position function. It's a rate of change of the position function. And similarly, acceleration also has a meaning. What's acceleration? Acceleration is the rate of change of velocity. How fast you change your velocity. That's what acceleration is. Velocity is how fast you change your position. Acceleration is how fast you change your velocity. So the velocity is the derivative of the position function. The acceleration is the derivative of the velocity. I wrote that at the end of Friday. So when you do this problem, to answer the velocity question, you need to take the derivative and plug in to get instantaneous velocity. And then to answer the acceleration question, take the derivative of whatever your velocity was, and then you plug it. Okay? Here we're taking derivative twice to get to acceleration. We call that the second derivative. When you have a function, you can take derivative 2, 3, 4, 5, 20 times, if possible. Okay? We're going to talk about those later. Those are called higher order derivatives. Where's my picture? Okay, here. Give me the same question. Okay, so here you just need to find the points at which, let's read it. List all numbers x at which the function graph above is not differential. Okay? So there's one that should be obvious to you. There is another one that could be a little bit less obvious, and that's why I wanted to show you this. Which one is the obvious one? -1. Why? Exactly, it's not smooth. There's the little peak in there, right? So it has a, like that, and then it falls very quickly. So that's not good. So -1 is obvious. Everybody see that? Now there's another one where it doesn't. If -3, very good. What's going on at -3? We have a vertical tangent line. Does everybody see that here, when you get close to -3, what happens is that your tangent line is vertical. So if you were to take the limit, if you have the formula, you're gonna get infinity in your limit. Do you understand this? So here the answers, the points would be -3 and -1. Okay. So just want to show you that because these functions are strange to produce. Okay, but they do show up. For example, the x cube function. Think about the cube root. Sorry, cube root function. The cube root function has this sort of behavior at the origin. Okay, it's gonna have a vertical tangent line. Okay, that's all.